about extending the Elasticsearch stack with machine learning. And then Matt Williams from Datadog over there. He's a DevOps evangelist, and he's going to talk about how Datadog leverages Elasticsearch. And then in between, we have Steve Kurtz from Elastic, who's going to introduce new graph capabilities in Elasticsearch. Stay tuned for that. So you guys can ask questions. It's open-ended. So enjoy the food, and thanks for coming.
All right, George. Yeah, thank you very much. So just a few words about myself. I've been in I guess software now for close to 20 years, which seems like a long time, despite my boyish face. I'm not actually a data scientist, although I do play one on television. So please be merciful in terms of the level of questions that you throw my way. I'll do my best, but
if you stump them, you can have a beer. So
that's right. If you
please
stump them, you can have a beer. So really, what we're going to talk about today is essentially extending the capabilities of the Elastic Stack and just, in some ways, just data in general with machine learning-based anomaly detection. And that really encompasses a wide variety of applications and use cases and lots of different things that you can do with anomaly detection. Prelert as a company, I've been there for almost 5 years now. I was pretty early on in the start of the company. This is basically what Prelert does. We are experts in this kind of machine learning-based anomaly detection. It's all that we do, basically. So, frankly, you better be pretty good at it. So let's kind of get into things here. And just out of curiosity, I'm assuming most people here are Elastic users. Is everybody pretty much an Elastic user? Yes? I'm assuming you are. Are you just learning about it, or are you actually using it on a day-by-day basis? Every day? Who uses Elastic every day? Okay. Good. How many people use it just for general, log management and operations? Okay. Does anybody use it for security operations, things of that nature? No? Nobody uses it for security? Somewhat? Okay. All right. Well, in general, right, obviously it's incredibly awesome to be able to aggregate data, be able to visualize it. What are some classic challenges that people have, right? So, if I'm looking at a dashboard and I look and I see there's a dip in something there, is that interesting? Is that normal? Is that what I expect? And if so, what about this other thing? Is that related? Is that useful to me? What about this one, right? So these are kind of the questions that people ask. And this is a classic data science problem, right? What to pay attention to when you have so many things available at your disposal, right? So collecting just gobs and gobs of data is a double-edged sword. You have everything at your fingertips, but then you have lots at your fingertips. So what are you going to do with that? So our whole mantra is essentially, okay, you know what? We're all humans, right? But we should allow some, machine learning to help us out. We're just mere mortals. So what are we talking about today? We're talking about this whole concept of essentially behavioral analytics as a high-level topic, right? So certainly anomaly detection is part of that. But specifically, what you can do with data that you already have in Elasticsearch. Sorry, slides are good. How we do it? I already mentioned this, right? This is basically fully unsupervised machine learning based on anomaly detection. Pretty big mouthful. So we'll talk a bit about what exactly that means, what's the approach, how that really works. But what's the point, right? Why? Why bother? right? So you want to be able to essentially get more insight out of the data with less effort, right? Less effort for you as a human. You want to put the burden back on the machines and on mathematics to extract out sort of some information for you. And going to benefit here, of course, is that if you're in sort of IT operations or log management, you have concept of like, I just get really essentially pretty good smart alerts that happen all on their own. Or if I'm in IT security, I can get sort of more advanced detection on things that might be unusual or maybe potentially threatening inside of my environment. Okay? So this is your typical Elastic stack. Did I get this right? This is pretty right. Okay. And on the right-hand side, there's the sort of the relatively newly branded XPath, right, which is formerly Marvell and Watcher and whatnot. Basically, value-added services on top of Elastic. If you think of Prelert, and what we do is essentially sort of yet another little building block there that again adds value to the overall Elastic stack. But I know you've heard me talk a little bit about anomaly detection. So, like, what kinds of anomalies, right? What are some sample anomaly types? And they kind of really span a pretty wide variety of different things, but they tend to fall into a couple of different sort of distinct categories, I think. One is that you've got a certain rate of expected things that are occurring, right? Whether it's number of orders that my website is taking, or number of hits on my website, whatever the case may be, there's sort of an expected pattern of that, and suddenly that deviates from what it should be, right? That's an anomaly. That's one kind. Another kind is the traditional, like, hey, I have a response time and suddenly I have a spike, or I have a dip in orders or something like that, right? Something that changes as a deviation of a value of something as a function of time. Those are both pretty easy to understand and sort of intrinsically they make sense to people. Another kind is a little bit of a special case, and what it is it's a rare occurrence of something. So what that means is like something doesn't normally happen, but suddenly it does, right? So it's like the novelty of something happening. Like, oh, I just got a bunch of error messages that said I can't connect to the database, right? That's sort of a novelty type of anomaly. And the last one didn't really have a sort of especially good picture for this, but this thing that's essentially I'm different, or this thing is different because it's not acting like the others, right? So this particular bird is not different because of its size or its shape or its species or its color. It's just behaving differently than its counterparts. So that entity is an outlier. Okay? It's sort of a special kind of way to think about an outlier. You're different compared to things that should otherwise be the same. Okay? So, how do you do this? How do you do this in a generic way? How do you do it in a generic way that's applicable to essentially any use case, right? Maybe it kind of falls into those categories, but for any kind of use case in security or operations or Internet of Things or whatever, how do you do it in a generic way, but effectively do it? Well, simultaneously being agnostic to the kind of data that's out there, right? There's all kinds of data. So how do you do that? The answer, and what our essentially mantra is to do it using predictions based upon probabilistic models. Okay. So, what does that mean? I'm sort of I'm really big on analogies, so Steve, you've only known me for about a month, and how many analogies have I pulled out of my rear end?
God, 10 or 15.
So here's a good way to think about probabilistic models. If maybe if you are a data scientist, I'm going to bore you for the next 5 minutes. But if you're not, this is a sort of intuitive way to think about it. Let's go through a little bit of a thought experiment. So, how could I accurately predict how much mail is going to be in your mailbox tomorrow? How can I do that, right? And how would I know that what you got was unusual? Okay, it's kind of an interesting sort of little thought experiment. How would I go about that? Well, for me to know if what you got was abnormal, first have to say, well, what do you normally get? Right? It seems like a logical conclusion. And so we would focus on a method that would first help us understand what normal is, and then we would essentially make predictions based upon a comparison of what we see versus that sort of established baseline of normalcy. Okay? So, constructing this model, what would I do? Well, I would sit on your porch, get out my clipboard, I watch the mailman come up, and I see him drop four letters in your mailbox. And I would go to my clipboard and I would write down, today is what? Today is Wednesday. You've got 4 pieces of mail. Okay? And I would do that for how long? Say, what if I did it for just one day? Just did it for 2 days. What's my guess for tomorrow? I'm going to guess what you got today, right? Unless I'm stupid. I would guess what you got today. It was probably going to get tomorrow. That would be sort of a really rough swag. And I'd probably be not too far off, but it's kind of a hopeful guess. If I sat on your porch for a week and I watched it for a week, do you think my predictions would be better? Probably. If I watched your mail for a month, would it even be better than it would be for a week? Yeah. If I watched it for a year, okay, maybe a year's a little overkill, but you kind of get the idea that the more time I spend and the more sort of samples that I see, the more accurate I'm going to get. So what are we doing behind the scenes? Well, what we're doing is essentially we're building a model, right? We're building a model of expected behavior in some ways. So these are just 3 sample probability models. The way to look at this is that across the bottom, these are the number of expected pieces of mail that I'll get on my, in my mailbox in the day, and the vertical axis is the probability, right? So, by the way, the purple graph got the best models in my house. I have about a 19 to 20% chance that I'll get between 3 and 4 pieces of mail a day. It's about right for me, and then sort of drops off after that. If I were a college student, I'd most likely maybe 37% chance get 0 or 1 pieces of mail a day, and then pretty quickly drops off after that. And not to really pick on my mom, but she gets a crap load of mail, so she's out there somewhere, with a slightly different shape to her mail delivery. So, what's the point? The point is that intrinsically we know that every household, or every entity here, really needs its own model, right? I'm different from Steve, different from Carl, different from Paul. Everybody's different, right? So we need to be modeled differently. So that's sort of in an intuitive sense. And the other thing to notice here is that each of these models have sort of different shapes. They're not, we always think about probability models. It says Gaussian bell curve, right? Well, not all things are necessarily Gaussian. They're not all that sort of nice bell-shaped curve. So that, every piece of thing out there may have a different shape. The other thing that you notice is that you don't need to rely on continued access to past data, right? I got my clipboard, right? I have my clipboard of what I have written down. The fact that you've recycled your mail days ago doesn't really matter anymore. I have information about what's happened, and that's the size of my model about what's happening is orders of magnitude smaller in size than the mail that's come through your mailbox, which is long gone, it's long been recycled, right? And we can use this information now to make predictions, right, about what's unexpected. So if I ask the question, hey, is 0 pieces of mail unexpected? Well, not for the college student, but it is for my mom. What about 15 pieces of mail? Is that unexpected? It certainly is for the college student, right? But my mom, she's got about a, maybe 3% chance of getting 15 pieces of mail. Okay, so you all have an intrinsic understanding of what this means. So let's sort of ditch the analogy and get back to sort of data in general, especially things that you might likely have in Elastic, whether it is events that represent things like successful or failed logins, or errors of different kinds, web access logs, or whatever the case may be, or if you get performance data, right? Response times, utilization, etc. These are all things that can be modeled very, very, very easily. So But here's the question as you, as someone is trying to work this out. How do you pick the right model, right? Because I'm saying that they all have different shapes. How do you pick it? Because if you don't pick the right one, if you don't model it correctly, you're going to have a bad time, right? You're going to have essentially bad results. So what we do is we essentially build the model for you, right? Based upon your data, okay? So we use a variety of different techniques to best fit the right model. So I know this is kind of small and probably you can't really see it in the back, but if you can see across the x-axis, there are a couple of little red X's along the x-axis. Those are, in this case, about 40 samples, okay? And the thin blue line is the best fit for the probability distribution of that. Watch how it changes as I add on to 80 samples and to 80 samples there and up to 400 samples. And you can see that depending on the data set, you can get a pretty complex looking probability distribution that may actually even be a mixture of a couple of different types, okay? And really, we go through great pains to this for one specific reason, which is if you have really, really good models, then you get really good results, and you have a lot less sort of quote-unquote false positives, because a lot of where the errors tend to happen is at the edges. And if you can model this correctly, then you're going to get better outlier detection in general. So we create these models automatically, very, very simply based upon essentially little recipes, if you will, right? We call them detectors, and these kind of map back to the things that we were talking about before about the different kinds of anomalies. And as you see when we go through the demo, we'll have the ability to essentially create these little recipes that are specific to your data. So, for example, if I have credit card transactions, I'll look for unusual amounts, right? I may apply a function, a function, to a field in the data, right? So maybe I'll look for unusually low purchase amounts, or I'll look for unusually high response times by host. Okay? So think of it in sort of you're structuring a little recipe to say, that's the kind of thing I want to care about in terms, for this data. Right? And from these detectors, we'll take care of the rest, right? So we go off and we build self-learn the appropriate models that accurately give you some good outlier detection there. Now, there's one more key step to what we do. And that is, specifically if your data is periodic, in other words, it's sort of maybe higher during the day than it is at night, more busy on the weekdays than it is on the weekends. If we see a couple of successive days and we sort of detect automatically that there's a natural periodicity to your data, we'll factor that in. We'll learn that. So again, I sort of apologize, the screen's not so big here, but the black signal in the middle is the actual real signal of the data. And the red and blue are sort of the upper and lower bands. And you can see that after a couple of days, we say, oh, this must have some periodic nature to this. So we start to try to follow the shape of the signal. And if you look at it across a couple of weeks, what you see is that those control bands, if you will, of what we predict should be expected gets tighter and tighter around the signal. And what this does, ultimately, it leads to absolutely incredible accuracy with, very, like I said before, very, very little false positives. So if I were to compare it on the left with a very, very traditional way that people often have done sort of prediction using things like Holt winners, sort of either like sort of based upon a moving average or an exponential weighted moving average. What you'll see is that on the left-hand side, sometimes, depending on the signal, you can get overfitting. And sometimes even like little sort of perturbations can cause, cause the signal to exceed or go below the sort of the predicted bands. And what you get is a bunch of false positives. Whereas, in general, our approach is a lot more accurate, leads to less false positive. And that's ultimately it's going to be more important because when you start to magnify this in a very, in a big data environment, you've got hundreds, thousands, tens of thousands, hundreds of thousands of things, even a small amount of false positives can lead to overload of hurt. Okay, so accuracy is a huge thing. Question, yeah.
What kind of probabilistic models are you using to sort of fit everything?
So the question was what kind of probabilistic models? So basically, similar to what I talked about before, we will do a best fit. So it could be we'll try several different models, whether it's a Poisson distribution, a log normal distribution, mixture must multimodal. So we'll try to see which ones sort of best fit that. We have our own internal calculations that look at essentially sort of error rates based upon that. Minimize the error rates, focus in on the right kind of distribution for that specific data set, and then select that moving forward. And by the way, it's not fixed, right? So as you see more data, it's allowed to sort of morph and change. It's not fixed in time. So it's not like a set training period where you're sort of stuck with particular behavior and you try to use that model over time. It's constantly evolving. So we have basically like an exponential sort of decay on sort of past learnings. So that allows the model to naturally drift as your data drift. Yeah, another question.
Can you elaborate a little bit more on how you're taking care of the periodic patterns?
Mm-hmm. So basically, in this kind of data, we really sort of put a whole lot of emphasis on daily and weekly sort of periodicity, right? So we use methods that essentially was described to me as sort of spline interpolation, where we try to look for essentially harmonics in the data that match sort of daily patterns or weekly patterns, right? And if we see those harmonics essentially exist, then what you can do is you can subtract them out, get residuals, then you can analyze the residuals.
So that's similar to you apply a Fourier transform and pulling the daily and weekly frequency components, using that as the baseline and do analysis on what's biased from the baseline.
Yeah. Yep.
Thank you.
Yep. And we tend to not go past that, so we tend to not go out of the box to try to do monthly fitting or yearly fittings. It just the benefit doesn't really outweigh the cost of doing it. Because obviously calendars are not necessarily predictable anyways. What was another question here?
Of course, in the graph, you can only show two-dimensional type of data frequency and some other axes. But if the data is multi-dimensional domain, is your best fit modeling?
Yeah. It turns out that we are now doing multidimensional distributions as well. So if you can imagine, sort of like the traditional way that people think about it is that you have like a cluster of points that are in X, 2 dimensions is easy enough to imagine, on an XY axis, and you have some outlier that's kind of over here. Its value is not unusual in X or Y, but X and Y is unusual. That's a hard picture to draw, but we're starting to do that. I think with our release this summer to do sort of multi-dimensional. Again, that's only when there's the situation where the measurement has to be unusual in more than one dimension together, right? Yep.
And when do you know your best fit modeling is not working? What if the data set is like a casino gambling and it's random and you have no way to do the best fit? And how do you know your modeling is incorrect?
Yeah, I mean, from a practical sense, right? the way that works is you can obviously send a vast sort of big time frame of data through in one fell swoop. You can inspect the results. You can see sort of the level, the signal to noise ratio on the output, and you can make a determination on that. In general, there are obviously different choices that you can make in terms of what aspects of the data that you do focus on versus others. Like I said, we have sort of an arbitrary nature in terms of what you choose anomaly detection on. Right? If there's fields in the data that are maybe not even sensible to try to analyze because they don't yield any good results. Right? If I look at, what's the just trying to think of something. Maybe I'm looking at web access logs, and I want to look at the cardinality or the differences in the length of the user agent string of the browsers. Maybe that doesn't really yield good results. That'll come out in the wash. Just one final note here on scale. It's one thing to say you're really good at just sort of anomaly detection in general. It's another thing to say that, well, I can do that across like tens of thousands or hundreds of thousands of things simultaneously and do it efficiently and do it in near real time. That's the key thing with the way that we architected everything such that we can do it in a massively parallel environment. And again, I apologize for the dark text on the dark table here, but if you look across, this is 33,000 distinct time series up to 133,000 distinct time series, and what you notice that the amount of memory our models take per time series is linear, so it's around I guess between 6 and 8 kilobytes per time series. So analyzing 133,000 distinct time series takes less than a gigabyte of memory in our processing. Okay. It's pretty fantastic. And in terms of velocity, talking about the amount of data per day, again, in this case, easily half a terabyte per day, just again in a linear fashion, so it doesn't necessarily suffer from the curse of dimensionality the way that we send. Yeah.
Does it run as a plugin in process with the rest of the Elasticsearch?
Yeah. So that's a great question because I'm going to show you what it looks like. Right. Any questions before we move on to the sort of the demo portion? How am I doing on time, by the way? Good.
We've got another 15.
Okay. Excellent. All right. All right. Okay. I might have to do that. Get this. This looks like this is super small, so I'm going to have to use the power of the Zoom here. All right. So what we've done is like I said, we've had this analysis engine in the works now for five plus years. Only in the last 3 months or so, we've put a lot of effort into doing a direct integration into the Elastic Stack. And it sort of manifests itself as a plug-in to Kibana. And the whole idea here is that, Elastic gives you access to a lot of good machine data. What we want to do is we want to create these we call anomaly search jobs that will routinely query Elastic for a certain sort of kind of data every X minutes, right? So going back to my analogy, it's like I want to look at your front porch and see how much mail you got today. Right? So do that every single day, every 5 minutes, whatever the case may be. So we'll have a variety of these different anomaly search jobs that are configured and scheduled to essentially run in the background and be able to, again, routinely inspect that data for you so that you don't have to have your eyeballs on the screen looking for those things that are unusual. So how does this work? So I'm going to create one of these new anomaly search jobs, and I will point this at a Elastic cluster. Now, in this case, I'm running all on one machine, but I can have this pointing at a remote Elastic cluster. So I can have a dedicated machine that's doing this analysis separate from my Elastic cluster, and then just remotely querying it and pulling it back. In this case, it happens to be all in one machine just for sort of simplicity's sake. And what I'll do here is I will just pick a set of data that is sort of representative of some from data from this case, CloudWatch. And go on to the next step here, the wizard. And just to orient everyone as to what this data is, again, try to make this a little bit bigger for people to see. Essentially, it's a bunch of performance data. Okay, so things like you have a field called metric, disk write ops has a value of 9.2, or an instance called whatever in a region called SA East 1. The next one is network in, got some other value here, so on. It's just a bunch of name value pairs. It's pretty easy, right? So let's go back. How do we want to analyze this data? Well, so what I'll do is I will add what we call a detector, right? It's essentially what I was talking about before, which is that little recipe, if you will. And what I'll just say, you know what, I just want to know them. I want to just see deviations in the mean value of that field called value, right? That's the numerical value that's in every record. And I'll do that for every metric. And if you remember, metric was network in, disk write off, whatever it was that we saw as the actual metric name. And I will partition it by instance. What does that mean is that I don't want to analyze all those as one big collections. I want to do it for every server, right? In this case, instance is a server. So think of it now. So let's say I've got 20 metrics per server. I have 20 servers. That's 400 individual things that we're going to be baseline, right? So just by virtue of splitting it out this way, it'll take care of itself and do automatically 400 individual baselines for that. Okay? One more step that I'll do is I'll say, this will come in later in terms of how we want to sort of view the output. We have this concept of a statistical influencer, and what that means is, okay, I'm going to detect an anomaly in some sort of performance metric. What contextual information might I want to know about that, right? Was it for a specific system? Was it for a specific region? Was it for a specific, whatever? So these influencers play a role into how it's going to be reported back to you. So I'll just pick instance, metric, and region. And what I'll do is, this is going to, I'll set up correctly. I'll say save. And I got to name it, dumbass here. Watch. Okay. So saving it now. Start the scheduler. So again, I'm starting from scratch, right? And I want to look at data moving forward, but I've got all this historical data from like months ago already stored in Elastic. Wouldn't I like to take advantage of that and have it look back over some historical data first and sort of build the models as if I had installed Prelert 3 months ago? Well, I could do that, right? So I could either start at a specific time and pick a time in the past. This is a kind of a relatively constrained data set, so I'll just start it at the beginning of the data set. But once it goes through all the historical data, it'll pick up and just start to request it every, in this case, I think I selected every 5 minutes. So it's doing that. It's starting to, you see that number there in terms of the number of data points that it's starting to process is going to increment. Just to give you a visual as to what that looks like, what's happening. So if you can imagine, right now is sort of time t. We went back in time, sort of bulk loading, bootstrapping a bunch of historical data, setting that data to our algorithms. Our algorithms store, just a clipboard, right? It's going to store the information about that data into an Elastic index. That's where we store our little models. Okay, and then once we catch up to now, then we only ask for data in small chunks, right? Only 5 minutes at a time or something incremental, okay? But while we do that, we load in our models that we've learned so far. So even though we're asking for only 5 minutes worth of data, we're comparing that versus a behavior that maybe I've learned over weeks or months, okay? we're going to analyze that, and we have another index in Elastic that stores our results. Were there any anomalies that we're seeing? How much? Where were they? What did it involve with? And that's what I'll show you in a moment, is what we display as part of our visuals. Okay? Now, if in the next interval we encounter some sort of anomaly, we repeat this whole process, right? If we detect that something is unusual, we will rank that on a scale from 0 to 100 based upon just how much of it unusual is it. Is it just a little bit out of bounds, or is it wildly out of bounds? Okay? So we have this notion of empirically scoring things based upon this unusualness in just one moment. Which presumably, it's not just a visual thing. You'll want to, physically maybe alert the watcher or some other mechanism, right? That you want to proactively notify that something's changed inside of my environment. Question?
What does that measure probabilistically?
Essentially, if you think about going back to my analogy of, is 15 pieces of mail likely, right, for somebody? I said for my mom, it's about a 3% chance, but for the college student, it's probably down to the 0.0000% chance. We take that probability calculation, right, which is we calculate out to 300 some odd significant figures, and we try to make that more of a friendly number. We sort of renormalize that on a scale from 0 to 100, where 100 is essentially the most unusual thing that's been seen. So we try to just refactor that probability calculation into a user-friendly number between a scale from 0 to 100. Okay? And that's how we sort of color our visuals. We color things. The things that are like red in our screen are things that have that score between 75 and 100. So it's a dynamic scale based upon sort of what's been seen over time for that data. We try to make it a little bit more sort of consumable. Okay? Makes sense? All right, let's go back. So that's still running. It's still going through, analyzing data. Like those cooking shows where it necessarily like whips up something and they throw it in the oven and they say, hey, by the way, I have another one that's already been baked. That was going to finish, but while we're you see, I'm smart. I know how to do it. Right? I'll look at one that I did earlier, just so I can get a sense of what the visuals look like. So if you bring up our summary view, again, for this specific job, and if you want to overlay jobs, you just select multiples. This is kind of what I was getting at before, which is if you want to focus on a specific moment in time here, you'll see that things that are blue are essentially, it's kind of like a heat map. Your data's not so hot, right? It's kind of cool. It's not so interesting. But if it starts to behave sort of differently, you can see this one has a score of 59, 92, and so on. And then down here, we also break it out. Remember I said those influencers help you with sort of understanding what's mostly impactful, who's to blame, essentially, for this anomaly, right? If I look at some of these, I can see that if I hover over the metric one, it says that the metric that's most influential on this unusualness is the top one, is the CPU metric. And as for region, the most influential one is SA East 1 as opposed to other ones. So now you're going to ask, what does influential mean, right?
Well, actually, I was wondering, is the top number, is that like representing the joint probability?
It represents a joint probability of those constituents. Exactly.
Okay.
Yeah. And also, what it also factors in is how many things out of the entire set are unusual together, right? Because like you said, I could have 400 unique things, 4,000 unique things being measured in one job. And what we're trying to express is that, do you have one giant gash in your arm? Do you have 1,000 paper cuts, right? Because they may sort of work out to being just as lethal, right? And you want to have an understanding of is it sort of one major thing? Is it a sort of a bunch of minor things? We try to roll it up and aggregate it as a joint probability. That's correct. Okay? So now when I drill in through this, now we get a little bit of a sense, again, of thinking about more detail around this notion of influence, sort of like who's to blame, for these anomalies. And I'm going to continue to apologize for the people in the back, but what these are on the right-hand side is that we've got a couple of different, remember we did 3 influencers, instance name, metric name, and region name. So at a glance, I know that there are a set number of instance names that are sort of kind of involved in this unusual behavior. So it looks like to be about 6 or 7 different instances. Instead of maybe one bad server, this may be encompassing sort of a bunch of servers at once. Under the metric, it looks like somewhat equivalent in unusualness across both the CPU utilization as well as the network anomaly. So it's sort of global across both. But key thing here is that I have regions in which I'm looking at this data across. It only seems to be affecting one region. So at a glance, I have a sense of like not only do I have problems, right? Do I have at least deviations in behavior? But I also know sort of where to sort of focus and narrow down things before I even get started. Okay? And then as for the individual records of things that are unusual, right? So, like I said, it could be, because of the way I did the configuration, I could be monitoring 400 things at once, right? Which of those 400 things are unusual? What specific metrics? And each of these records here for this time frame, they also get their own individual score, right? Like, as you mentioned before, there's sort of the joint score that's rolled up. But for every little item, they also have their own score. We score everything. So if I look at sort of the most egregious thing, we'll see things like the fact that, bigger here a little bit, this specific metric, network in on this specific instance had an actual value of about 6,400, whereas typical value is it's up in the 7 figures. So it's a lot less than what it normally is. Okay, we're agnostic. We don't really make any judgments based upon the actual metric, and that's like this is in megabytes or anything like that. Say we just look at the raw value, say it's less than what it normally is. Okay, so what we've collected here is a bunch of related sort of clusters of things that are happening all around the same time. And we also give you the ability, if you want, is you can link back out to a standard Kibana dashboard that you have maybe already built for that specific collection of things. And we've already pre-filtered it with that specific instance name, in this case, that region, right? So now I can say, holy smokes, there really was something that changed during that time. I can see everything's, for this instance, sort of all changing its behavior at once. If I go back a few hours here, go back to 9 o'clock. I can see that it definitely was a distinct time where there was a behavior change to that. Again, this kind of anomaly detection is not judgmental, right? It doesn't say this is bad. It doesn't say it's good. It just says it's different, right? It just says that it's not behaving like it normally does. There's just been a change of state. Okay, so now it's up to you as the operator to say, I want to make a judgment based upon that. But the fact of the matter is that, and this is where we're getting back to this idea of the more data that you give it, right, the more confidence it has that what it's finding is truly unusual. Because if it sees this sort of pattern on a day-by-day, week-by-week basis, it'll learn that that's normal, and you won't see this in the future. Okay. There's a question?
Yes. So I see what you presented. Correct me if I were wrong. You have a lot of these influencer. You thought it was an influencer. You see their behavior pattern change, and you thought they contribute to your overall what you are trying to detect that change. But I still don't see how do you know that influencer, their change behavior is contributing to your overall change. I
So
don't see that relationship.
Yeah, so how the influencers are actually under the covers calculated is that we look at the anomaly. We look at the information leading up to the anomaly. And if there are if in that time frame, there's data being contributed from multiple instances of something, we know what the contributions are from each of those instances. And one by one, we'll subtract the contributions from that instance out and basically ask the question, is it still an anomaly? If you subtract it out an instance and say it's no longer an anomaly, then therefore the one that we subtracted out must be very influential as to the anomaly. Does that make sense? So that's where this notion of an entity being potentially influential on the anomaly is because if you remove it and the anomaly essentially goes away, then therefore it must be contributed to the behavior.
So in your calculation, you have a background process to the what if analysis.
Yeah, way in the back, question.
Right. So you just said that you do not make any judgment on the anomalies, but would it be possible to teach the model to differentiate some different kinds of anomalies? For instance, it's Wednesday and there is no mail in the mailbox, and that's because the mailman is sick. Like, it's not something. So if you're trying to look at the anomaly you can action on, this is not something you can action on. So maybe you don't want that to be going back all the way to you. Maybe you want to
So this repeat for everyone to hear that. Basically, the question was: is if you have a bad day, right? The mailman's sick, you didn't get any mail.
The database is dead.
Right.
That's why your service is good as well.
That's right. So essentially, there's either a problem in the data, or you have an unexpected black swan style event, right? There's something. So there's two things to look at that. And one of the items is that does an event like that sort of poison the model for a long time? And first of all, the answer is no. The way that we do things is very Bayesian way, and the level of contribution to something is proportional to sort of how much has been seen so far. So we don't let a single event like that wreck things. So that's one thing. We can essentially unlearn something as quickly as we learn, especially if it's novel. That's one thing. Second thing is that if for some reason you do have a problem, we've had customers that have this where they said, you know what, we just had some catastrophic thing that happened. We had a really bad day. Maybe it's not going to wreck the models forever. It's going to make them at least out of whack for at least a couple of days. Can we at least revert to what we had yesterday? Sort of forget about what happened. Sort of like revert the model to sort of one day prior. So we have that facility to essentially revert back to a previous snapshot of the model. So if you really do have a bad event, you can sort of essentially say, wipe that and just pick up where you left off one day before that happened. That's the second thing. The third thing is that kind of getting into this idea of I want to help, right? I want to help the model. I want to sort of teach it a little bit. And that's where you sort of cross the line a little bit from what we're doing right now, which is unsupervised machine learning, into supervised or semi-supervised. And there's merits to it, no doubt. And we're dabbling in that. You just need to do that in a very, very careful way. Because if you don't do it in a careful way, then what happens is you have potentially a bunch of recommendations or human inputs to something that leads down a slippery slope where somebody does a bunch of things, you don't know why they did them and why they counted this thing as good or why it's bad, and then you have a legacy of sort of potentially bad decisions or unknown decisions as to why somebody wouldn't have picked that, right? So, but we're dabbling in sort of the semi-supervised things because you're right, there is some tangible value in that as well.
It sounds like your model is assuming that the series are all independent. Is that right? And if so, doesn't that lead to overestimates of the significance of some events when the series are correlated? You have some underlying value go out of sync, which drives a whole bunch of your series out of sync.
I don't know if I can accurately answer that question or not. I mean, I do consider things independently in terms of the way that we model things, but how we aggregate the scoring, right? If those items are together in the same job, do take into account the fact that multiple things are being unusual together. Now, I don't know if you're trying to get at if it's significant whether or not one causes the other, or
No, it's more. So suppose you just put 100 instances of the same variable in there.
yeah.
Like so, 100 time series which are identical, and so then if you any variation in that, if it looks a little bit unlikely with respect to the probability model for that particular series, you're just going to get that probability raised to 100, and it's going to look very unlikely. Does that happen?
I imagine you could contrive a situation where you're doing that. I think probably where the fault is in that is in the case where you wouldn't normally do the same thing 100 times. But
Right, but you're going to have a lot of series that are correlated. I mean, the variables that you were looking at there will often
But that,
correlate.
but that very often is a good benefit, right? If you want to know if in other words, if one metric, is the tree that falls in the forest and no one cares and doesn't have any other downstream effects on it, it can be a bit of a so what, right? But if there are multiple things that sort of move because of that and they all perturbate together, that's in general usually a lot more interesting than one specific item on its own. So I can imagine where you pose an interesting question, but I think that in a practical sense is probably a good thing, right? That you elevate the score in proportion to the number of things that are unusual together.
So, do you know whether the joint model that top line value is calculated from, does that assume independence of the time series? Or?
I can't accurately answer that question. I mean, I can. Why don't we exchange contact info after, and I can ask the PhD that knows the answer to the question, right? But like I said, all I know that it's that top level sort of score that is aggregation is a joint probability of the items that are together. Most likely, it probably assume that they're independent, but I can't. I'm not concerned. Yes.
Do you have any way to configure the sensitivity of a given model?
There are some tweaks that we're experimenting with. Specifically, one of the customers that we're working with now, if you can imagine, for example, if you have a time series that maybe is disk IO or something like that, and it's always 0 for an immense number of time, like the latency number is 0, and then suddenly it goes to 3 milliseconds. Relatively speaking, that's still unusual compared to 0 for weeks and weeks at a time, but 3 milliseconds is still pretty low in terms of the latency number. So it's kind of like, yes, it's unusual, but I don't really care. So we're also experimenting with this idea of having, you can inject yes, but as long as it's below 100 milliseconds, and only show me deviations that are significant and that are outside some sort of sort of control. Again, it's kind of getting back to injecting a little bit of sort of human intelligence. Yeah.
So in this case, was it not better just to have a threshold of 100 milliseconds?
Is it not just better to have a threshold on things? Was that the question?
Yeah, for the specific.
Well, I mean, let's be honest. I mean, there are some things out there that absolutely, if you know that something should never be below 50, if you know the number of orders that your website takes should never be below 100 per day, then by all means, put a threshold on that. I mean, this is not a replacement for things that you already know. Just in general, people use this more as a safety net on the things that they haven't gotten to figure out what's the right thing to put thresholds or alerts on, right? So I've got people only tend to put, knowledge into less than 1% of the things that they're collecting, right? It's the other 99.9% that usually need to have some sort of coverage. Sorry, did you have a follow-up question?
Yeah, it's unrelated.
Okay.
It's kind of a UI question.
Yeah.
Are you able to display multiple models on the same page? Because that would be incredibly useful for root cause analysis.
Well, you can pick multiple analysis jobs, which may have different models. So you could look at, for example, I could look at results of, for anomalies in my application logs for unusual message at the same time as looking at performance metrics. Or, yes, you can overlay those and be able to see sort of vertical views of like, yes, there's a confluence of problems across these 4 kinds of data. Absolutely.
How
Yeah.
do you enable the anomaly detection? How do you enable the anomaly detection on Elasticsearch? Is that a plugin? Is that an installation?
You go to www.prelert.com and you download the product. No, it's a plugin. So it's a separate product. We're these as of right now we're independent from Elastic as a third party. Maybe someday it'll be built in. That'd be cool.
Good luck.
I feel like I've dominated a lot of time here. I know we've got some other speakers. Any parting thoughts? Awesome. Thank you. Thank you so much.
Matt, you need 30 minutes, you said?
Yeah, 30.
The new products that we're adding to the suite of to the Elasticsearch. It's actually graph capabilities. And so very quickly I'll give you an overview and then I'll just jump into it. When we started thinking about this graph product, you can sort of think of the origin story. We recognize 2 very simple facts, and it's going to seem obvious, right? Your data is not flat. It's referencing real things in the real world. In a tweet, you've got a person, you've got a location, you've got other things like a date, potentially hashtags or topics, things like that. And all of these are properties. And if you think about this, you can sort of think of these as actually not just like pieces of data, but as relationships between them. So you can imagine different types of relationships. So the fact that my name and my location co-occur in a document, that's saying that this person is in this location, or at least claims to be. And so that's one piece of evidence, that's one relationship between me and that location. Another type of relationship would be an indirect relationship, where across different documents, I say I'm from Boston, someone else says they're from Boston, and the fact that we both share that property is another example of an indirect relationship that's represented across them. And when you start to think about these, the fact that you've got all this information modeled after real-world objects, and the properties are actually representative of links between those real-world objects, you can start to do some interesting things and actually ask questions about the relationships rather than about the documents. And so that's really what our graph product is about. So there's lots of different use cases for it. I won't go into them now, I'd rather just sort of show you. But there's a couple of different things. I think this is going to change the kind of question that you can ask about your data. And I think you're going to find that if you're right now building machine learned models for building recommendations engines, that asking questions like this might mean you don't have to do so much of that. Or if you always wanted to, this might be an interesting place to start before you go out and invest in machine learning people and infrastructure and process and so forth. But this isn't magic either, so it's not going to work in all cases, right? So it's a very complicated set of math that goes on. But basically, we're trying to do 2 things. The first thing is let you ask questions about those relationships. So just, first of all, can I ask a question about the relationships rather than about the data? Then the second thing is, can we give you more relevant, more interesting results? And there's all kinds of problems that come up when you start to think in terms of relationships and graphs and things like that. You end up with these super connected entities if you think about these things. If you look at Wikipedia, everything is like a hop and a half from United States. So if I'm trying to use the graph of links between Wikipedia pages to tell me something, almost no matter what I do, if I'm basing it just naively on the count, the number of references, everything is going to pull me towards the United States, pull me towards living people, pull me towards these other super connected objects. And so what we're trying to bring to the table here is something very different. Using the same sort of information retrieval techniques we use to do relevance ranking for search, we keep track of all the statistics, the document frequency, how many times does this property of the real-world object occur in this document versus the overall set of documents? And can we compare not just one document, maybe a subpopulation versus the global population of documents? And with some of that math that we're already collecting, that's already in the indexes you have, you can ask these new questions. So what we built is a simple graph exploration API. And basically, you can start to say, well, yeah, I'll just show you. You can start to say, I would like to run a query against the last.fm data set, a public data set we'll look at in a moment, and I'd like to explore it, and I'd like to anchor my query on Mozart. And then I want to explore out from Mozart, right? Looking at the artist.raw field is where I'm going to start, and I want to link that to other artist.raw. So I actually want to use this data set to actually recommend me other musicians that are similar to Mozart. And this is the API. It's anchored with the Elasticsearch query language, but it actually lets you speak, talk, and get answers in the form of graphs and relationships between the properties and entities. So with that, let me just give you a quick example, and then we are done. So if we take a quick look, so one of the things I mentioned before, these super connected entities, in almost all data sets, you have this notion of like Zipf's law, where like you've got this sort of like power law distribution of like super popular things at the top, and it scales down very quickly, and you're in the long tail. We see this almost everywhere. So in music artists, number one in this set of music data is Radiohead. If we look all the way for number 50, the long tail is Michael Jackson. It's like, really? Long tail? I wouldn't have thought, but there it is. You see it in Best Buy search data. On the way left here, we have LCD TVs, and on the way right, you get down to modems. And you can start to see, how that distribution goes. And so if we use this, you can see it in other places too. In Stack Overflow, all roads lead to JavaScript. In Stack Overflow, kind of weird. Must be quite popular. But so if we actually now start to look at that data, let's use the music data for one example. We've got a bunch of others that we could look at, but let's just do one in the interest of time. And let me grab the index. So this is a Kibana plugin. It's shipping as a Kibana plugin and a Elasticsearch plugin. Elasticsearch plugin gives you the API. Kibana gives you this UI that we're looking at. And so we grab the index that we're interested in. We look at the artists, and we do a search for Mozart. And what I want to do first is I want to turn off this thing. I want to show you what would this look like if we were not using relevance. If we're not using relevance, we're going to be pulled towards those super connected entities. And so when I run this search for Mozart, what we are going to see is we've got Mozart here, we've got the Beatles, we've got Coldplay. It doesn't seem like a very good recommendation, but these are the super connected entities. They just occur so frequently. So if we were to actually look at the link, there's 773 people that like Mozart and also like Coldplay. You can see it represented in the sort of Venn diagram. But you can see that like the Coldplay Venn diagram circle is huge. The overlap is very small, but the actual number of people that like both bands is quite high. Whereas if we were to look at something like the link between Mozart and, if I can get this here, there we go, the link between Mozart and Bach, you can actually see circles are more similar sizes and the overlap is a much larger overall percentage, even though the total number isn't all that much different. And so what we're trying to do here is relevance rank, and right now it's not going very well. So if I turn on this relevance and I run this again, what we will see this time is it's going to be a set of relationships that are much more targeted for, in theory we will see, this is what I get for attempting the demo guides. If this doesn't work, you'll just have to take my word for it. There we go. And so here, when we look at these relationships, we actually see that these ones are very much appropriate for the recommendations. These are all classical artists. And if I expand the chart out from here, you can start to see we're adding more musicians, more links between the existing musicians, but it's all really relevant to the query that I anchored it with, as opposed to exploring out, hitting the Beatles, and then going off towards all kinds of strange pop bands. And so this is what happens when you bring relevance to graph exploration on top of Elasticsearch. Same indexes, new way to query. The end.
Steve,
Questions?
how do you compare that to something like Neo4j? Like how do they overlap the capabilities? Would I use this versus Neo4j for different things? Do they have matching?
Yeah. So I actually think of them as complementary. As there is a bit of an overlap. So if you were thinking about maybe starting to work with graph or think about your data as graph and you haven't started yet, this might prevent you from wanting to invest in the complications and overhead and complexity of that. But I see in a lot of cases the sort of like path walking, fancy, Sparkle or Gremlin or all these other graph APIs that give you, I want to walk from here to here, and then I want to take, only follow links with these properties and then come back and then link back to the original place where I started. Things like that we're not trying to do. This is a very narrow exploration API, so saying start with one or start with a set and explore from there using relevance sort of as your guide. And that relevance piece is the differentiator here. And the fact, of course, it runs on the data you've already got. Yeah. Question in the back and then one?
Just a question for the specific example. How do you build the relationship from?
I'm sorry?
How do you build a relationship between the artist and this one? Is it from the link on Wikipedia's or is it people talking about it on Twitter?
Yeah, no, sir. Yeah, I didn't show you the data. So this one, it's actually, Last.fm published a set of data. It's properties of each user, so it's like 3 or 4 million users. And you've got their age, their gender, their country that they're from, and a set of their top N bands that they listen to. And so it ends up being a very simple data set. I can show you after if you're interested in the model. But yeah.
So if I understand correctly, you're doing only one edge for this graph analysis?
Right, in this example you can't actually do multiple types. So I could be exploring, for example, if I were looking at network traffic data to my website, so weblog data, I could be looking for, show me, let's take a known attack vector. Let's say people making requests for /admin on my website. And then I want to say what IP addresses are making requests for that, and then what other things are those people uniquely making requests for. And because we're using this notion of uniqueness or relevance, we can start to say, who is uniquely asking for admin, and then what are those people uniquely doing other than admin? And you can actually, it's kind of neat, we learned some new attack vectors for one of our engineers, like public websites that he runs. So it's kind of fun to see, knowing that script people will just start hitting your /admin to see if you've got an admin console or something. They'll also go to all these other different, maybe less well-known attack vectors that you might not have been aware of.
So you mentioned relevance. I was wondering what kind of score is used for this.
Yeah, it's you can think of it as the same sort of way that we calculate relevance for search, where we're using statistics like the term frequency in a document versus the inverse frequency of the overall set of documents. So for the given field that we're looking at, it's we're trying to come up with these that essentially do the math to say what's different about this population versus the global. So we're actually taking the terms in this document, this set of documents, and saying how frequent are these terms, or in fact these links in these set of documents, and how do the frequency of those compare to the frequency overall? Because at the frequency distribution in this set of 100 or 200 people that liked Mozart, if they all like the Beatles and everyone everywhere likes the Beatles, that's not as important because they like it at the same rate. But if they like the Beatles way more than the rest of the population, then okay, that's likely to be more interesting. And so the math is complicated. Honestly, I don't fully understand it, but we could certainly talk more about it in the interest of time, maybe offline. More here.
When is the data stored in? Back end, where's the data?
The data lives in Elasticsearch. So this is just a new API on top of Elasticsearch. So it's plug into Elasticsearch that gives you a graph API. And then the UI that we were just looking at is a plugin for Kibana that gives you the graph user interface, basically. One more back here.
Are you using the significant terms aggregation behind the scene?
Yeah, so we're using that and a whole bunch of other math, but that was actually the same guy who developed significant terms was the guy who developed a lot of this same math as well. So you can imagine an example like this with a single field, it's pretty easy to understand. Say, for one link, you get significant terms in, hop from there. But when you start to go multi-field, the math multiplies and gets a little bit more complicated. But yeah, absolutely. And in some ways, it's very similar. So if that makes sense, like you can imagine this being powered by significant terms on steroids, if you will, and applied to the graph problem.
There's a great webinar you guys did about this.
Yeah, that's true. Yeah,
available.
Yeah, that's on the website. So we did a webinar last week.
So we can put it on the meetup.com site for today's meetup in the comments section. We'll post a link to the webinar if you guys want to check out offline. It's about an hour. It's great. So
yeah, it's great. And it's demoed by the guy who wrote the software. He's much better at it than me.
Thanks, Les.
Cool. So I'm here to close out the session. Don't worry, my topic only takes about 4 hours, which should be out of here by midnight. No problem at all.
Oh, really?
Yeah, we can schedule a meeting.
Yeah, there we go. Okay, my name is Matt Williams, and I am the evangelist here at Datadog. And we, at the beginning, so we're the guys hosting. So thanks so much for visiting. We're the first large group that has come here, other than employees. So it's very exciting to have a whole bunch of people who don't work here. Let's see, what else? Hopefully you all found the beer. Hopefully we did good on our beer choice. Hopefully we did good on our kale pies choice. Yeah, in fact, by the way, we are hiring. We are excited to we're always searching for more people, and we tend to get stuff like this for lunch, 3 days a week, something. We're hiring. Elastic at Datadog. My name is Matt Williams. I already mentioned I'm the evangelist at Datadog. You can reach me if you have any questions about this. Matt.williams@datadoghq.com, or on Twitter, I'm a techno evangelist. And so what I wanted to show here was how do we use Elastic here at Datadog. Elasticsearch is actually a pretty big part of what we offer. Now, what do we offer? Well, we're a SaaS-based infrastructure monitoring product. The idea is you load up an agent on each host that you want to monitor, and we start collecting metrics and events and stuff about what's going on in your environment. We've got about 120 plus integrations. I put plus because every week it seems like we've got a couple more. One of those happens to be Elasticsearch. But there's all sorts of others, like maybe Chef, or Cassandra, or Ansible, or I can never think of all of them when I'm up in front of 40 of my best friends. So we're collecting all these metrics, and we collect a lot of metrics. We've got thousands of customers, and that ends up being, we collect billions of data points every day. Now, this number is another thing that keeps changing. When I did sessions, say, a year ago, we were getting close to about 1 billion data points a day. Then when I did a session at reInvent for Amazon back in November, we were at about, I think, somewhere around 12 or so billion data points a day. When I handed this slide deck over to my CTO, just to verify I'm not sharing too much, he said, looks great. One more thing, you got to include how much data we're pushing through now, because we're getting close to 1 trillion data points every day, which is, oh my God, so huge. We went from 12 to 1 trillion, 12 billion to 1 trillion in a few months. So awesome stuff. And then events, so those are data points like CPU utilization, 90 or 70, or those kinds of things that we're collecting. But we're also collecting events. Docker came up, Elasticsearch came up. Elasticsearch had some kind of summary of log data. And we're processing millions of those events every day for our customers. But actually we use Elastic in 2 different ways. We've got a customer-facing product, which is our event stream. And then we're also using it internally for all of our logging. All the application developers build out some sort of cool tool, and they want to log that, and they log it to Elastic. So let's talk about both of those things. First off, the event stream. Now, when you first log into Datadog, you can set one up if you want. It's a 2-week free trial. But anyway, when you set up your account, you log into your account, you're usually going to see your event stream. And your event stream is a list of all the things that are going on in your environment. It might be, hey, there was a GitHub commit. There was a Jenkins deploy. There was a Chef pushing out thing. There was a Docker came up. All sorts of events that show up in that event stream. Now, we used to use Postgres for this. We used to use Postgres in one massive table. That didn't scale very well. And so we're having all sorts of problems. You may want to make any sort of changes to that. Change a column, change for whatever you were trying to do, that meant taking events offline. Basically, couldn't write to it anymore, so we could make any changes and then bring it back up. Not a really good scenario. So we stopped using that 3 to 4 years ago. Our event data, pretty structured for the most part, and we're processing billions of full text events across 12 indices, basically one for every month. One for every month plus one in the future because we sometimes get events from the future. And then we also do alerts and notifications. So you can set up, I want to get alerted when there are 15 of some sort of event or some sort of log entry that comes in within 5 minutes. I want to get alerted on that. So that's kind of what we do for the event stream. So let me show you the event stream. This is a screenshot, a little bit, well, so I pixelated some things that were a little bit sensitive, but then I realized this is a smaller screen than I was, even though I'm here. It's a smaller screen, and some people are far away, so you can't see anything anyway, so I'm kind of secure anyway. But this is the event stream, and the event stream is split up into, several sections. First off, the big thing in the middle is the event stream. These are all the events that are being processed by the system. And so you can look at this event stream to see what's going on right now. You could also, if you've missed yesterday, you can look at yesterday's event stream to see, well, what was the health of my system yesterday? So it's kind of like an ongoing documentation for your environment. Pretty cool. You can also start up conversations here and all sorts of other cool stuff. Over here on the left, we've got all the event sources. So this is mostly what we use for production at Datadog, along with a few other things that we're currently building out. Up at the top is an aggregation of all our events. It can be really easy, quite common that you log in and you look at your event stream and it looks like everything's red. Everything's a disaster because the first 4 or 5 events are all some sort of error. So it could be easy to assume, oh my God, it's really bad, I need to quit. But the aggregation at the top is really useful to provide some context about what's really going on. I can say, okay, yes, these 4 things are really bad, but generally, things tend to be pretty good over this 2-day time period. Okay, well, maybe it's not the end of the world. Up at the top, I can do some search, full text searching, as well as based on sources, data sources. And then I can choose what kind of date range I want and go back in time. You can do all sorts of searches based on sources. These events are coming in from GitHub or from Chef or from other users. These are coming in from specific hosts. I only care about this set of hosts or this region, this AZ, whatever it might be. So how do we do it? We've gone through a few different versions of our Elasticsearch cluster. We started out with one node per AZ, kind of handling all the HTTP requests as well as the data. And we had this pool of nodes that we could write to. We're writing all the time. And of course, we had one index. You'd think we'd learn from that Postgres mistake. One table for everything, didn't really do so well. And we tried the same thing with Elastic. Elastic's supposed to solve world hunger, so maybe it's going to do something amazing here. But we ended up having to change things after about 1.5 years. So it didn't quite solve all our needs. And so we split the cluster into head and data nodes, about 20 nodes per cluster, about 2 replicas per shard. And the head nodes are purely a load balancer, purely taking in web requests. And the data nodes are doing all the writes and reads, searching of data. So those head nodes really handle a lot of the a specialized kind of work, whereas the data nodes can just do what they're really best at. And then we use a rolling index with 1 month of event data every month, plus 1 in the future because it's there. Sometimes we get events from the future. And so this is generally how things work. Alerts and notifications. As I said, we wanted to be able to alert based on 10 events of this particular type come in within a 5-minute period, shoot out some sort of alert. Originally, when we added this feature not that long ago, a few months back, we were concerned that maybe this is going to take too much from Elasticsearch. We don't want to, the event stream is a core part of our product. If we screw that up, that would be bad. So let's set up some other set of machines to be able to process all of our other queries, our alert queries. And it turned out that was kind of a silly thing to do, and we ended up rolling back and just having Elasticsearch handle all these queries. And what we found is, we have now thousands and thousands of these queries that are running basically every 15 to 20 seconds, and each cycle of all those queries takes much less than even a second. So that was really, really wonderful. Okay, so that's one use of Elasticsearch inside Datadog. The other use of Elasticsearch was for our internal logging purposes. So we were using some third-party logging tool, and we wanted to get off of that. Third-party tools are great once you get to it, until you get to some certain size. And we were getting to that size and seeing that build, and wanted to move on to maybe build our own service. Maybe we could do it. We had a specialized purpose and do it better, cheaper. And we wanted to provide a service that was provides structured search, be able to graph the search results and log dashboards, create dashboards based on those logs. Log stats and events to Datadog as well. We're a monitoring company. We've got pretty graphs. We want to see this stuff in our graphs. We wanted to decrease the need for developers to log into different boxes, do distributed greps. Generally not a good idea. We wanted to give them one place to go for everything. We wanted super fast access to the latest data, basically today's data. Pretty fast access to the next 6 days. So we've got 7 days that is really pretty good or really fantastic. And then, pretty good access, but okay access to everything older. Again, migrate off that previous logging tool. And so basically we handle about a couple of terabytes of data every day, of log data that gets added to Elastic, averaging about 150,000 events per second. And then that occasionally spikes into the 20 million or so events per second. And this is done through a combination of the application log to syslog to rsyslog to EBS mount to Kafka to Logstash to Elasticsearch. Now I'll kind of pull that apart a little bit in the next slide. Now each of these stages is kind of a little bit of a buffer, just in case the next stage can't quite handle the load. And also adds a little metadata, kind of figures out what the data is, and just adds value. We use Curator to tend to all those indices to make sure that as indices get old, they get moved on to the other nodes. And we use an idea called fast and slow nodes, or fast and slow nodes that we learned about from a blog post actually by another Elastic user called Chartbeat. And they wrote up a blog post about how they use Elasticsearch. We learned a lot about how they did it, kind of added it to our own environment. So this is kind of the flow. Got an application, and all that the application developer has to do is write to syslog. That's easy. There are plenty of tools to make that easier. And so I don't have to know anything about Elasticsearch when I build my application. All I need to know is write to syslog. Now, rsyslog is listening locally for syslog messages, adds it to rsyslog, and then hands that off to an EBS mount for certain types of data, for auditing logs, audit logs, and for other data that we need to keep around in its original format for a long time. Maybe a year, 30 days, whatever that time period is. And then we also hand it off to Kafka, and Logstash is going to be has a consumer for Kafka topics, and we push that into Logstash. And then Logstash, does its little munging and hands it off to the fast data nodes, which are just holding 1 day's worth of 1 day index. And at the end of that day, gets handed off to the slow data nodes, where those indices sit for another 6 days. And at the end of that, it gets handed off to S3. And so when stuff goes into the EBS mount, or at the end of 7 days, They all end up in S3, and then we've got cron jobs to kill off data as to certain time periods. So for some data it's 30 days, some data it's a year, and some data we keep around forever. Well, for us, forever is 5 years so far, and maybe forever will be forever. I don't know. So how do we monitor all this? We're a monitoring company, so we're obviously going to be using our tools for monitoring Elasticsearch. That said, we do use the other part of the Elk stack. We do use Kibana as a front end for our Elastic cluster. Okay, so how do we monitor Elasticsearch? This is a dashboard. Now, this isn't the way most people look at the dashboard because they'll be looking at it much bigger, and they'll be using scrolling up and down because that's what we can do on a interactive interface. Whereas in a slide, you want it all stuff in one page so you don't have to scroll around. But this is generally what we're looking at. So I asked two of the guys who were most focused on managing our two environments for Elastic. And I asked them, well, what are the metrics that you focus on most? What's the most important stuff that you keep an eye on just to make sure everything's working well? And the metrics they talked about were current HTTP connections, grouped by node and by head. And so you see the three different heads colored there. User CPU on the data nodes, and it's done as a heat map. So the darker colors are where there's more instances with that value, and they are generally pretty low. Network in and out by node. Oh, by the way, you are noticing that I've got rid of the X and Y axis. That's on purpose because it's kind of secret issues with the sun. So we don't share that, but we are interested in sharing how we're monitoring. So the other thing is JVM heap used by host. Shards by status. So we care about not only how many shards there are, but we want to see by status. They're all at the same status, they're all doing okay. But if we see others that have a different status, it'll be pretty obvious when we look at this. JVM garbage collection time by node, and fetch query index rates for the cluster. And for some reason, I have JVM garbage collection time by node twice. It's not to say that it's twice as important. I just forgot to leave it. Anyway, here's another dashboard we use. This is a little bit more redacted because I was told to. But the kinds of things we're looking at might be the query rate, indexing rate, number of events that we're collecting per day, nodes and data nodes and active shards, and how long indexing time and query rate, and all that kind of stuff. So these are dashboards that these two folks and a few others look at every day just to verify everything's going well. So I'm going to end with 2 slides of tips and tricks, things that we have learned about setting up our Elastic environment. First off, read the documentation. Okay, it's kind of obvious, but really, read the documentation. The reason why is there's a lot of good stuff in the documentation. Second point, no really, read the documentation. So there were several instances where these guys created this cluster, they looked at something in the docs and thought, that doesn't apply to us. Let's do it some other way. And they start doing it some other way. Oh, yeah, documentation was correct. We should have done it that way. Let's go back to the way the documentation says, hey, it works a whole lot better. So read the documentation and actually abide by it, where it makes sense, most of the time. Read and review how others use Elastic. We found all sorts of great examples of how people are using Elastic. I mentioned Chartbeat. You can look on the Elastic site for all sorts of case studies from Elasticon from January. Was it January? February. And there's a whole bunch of case study presentations on how people use Elastic. Awesome stuff.
Like meetups like this.
Meetups like this, yes. Give some planning time to sizing. If we had spent a little more time thinking about it, we wouldn't have had to re-architect to go to one index per month, or per day for internal logging. You look around online, you look at how other people are using Elastic, you see that that's kind of a common use case, a common way of setting things up. And we didn't spend enough time planning ahead. We're a startup, we're trying to run way too fast. You're never going to get things right the first time, so architect with migrations in mind, because you're going to screw it up. Hopefully you have a plan in place to make sure that you have something better to move to. And of course, we're a monitoring company, so you'll want to monitor from the beginning. We found that monitoring super useful because we make a change, and we want to see if it was a good change. We want to see if we made things better or worse, and we can't really do that if we don't have some sort of monitoring solution in place to let us know, okay, we're doing the right thing, or we're not doing the right thing. Tagging can be a little odd, but worth understanding. And when I asked one of the guys who set this up, well, what do you mean by that? Well, we set up these hot and fast and slow nodes, relying on tagging for how these things scale, and you add a tag, and then you want to delete a tag, but you can't delete the tag. It's just kind of almost like a tombstone. Basically, it's there, but not. And it reminded me of like Active Directory. If you added things in Active Directory, they kind of live there forever, even if you want to get rid of them. Something I used to deal with when I was at Microsoft a long time ago. Next thing, devour everything you can about JVM tuning. Kind of a black art. There are things there you read online, you find 10 things, they all point at 10 different things to do that are completely against each other, but try them out. And of course, because you've got a monitoring tool in place, you can see if they actually made a difference. Make sure the CM, the configuration management tools, get it right. Okay, it's not so much the fault of the configuration management tool, but rather the person who sets up the configuration management tool. One of the mistakes we made is that apparently it didn't quite understand the difference between the head and master data node, and got them wrong, and there were all sorts of problems that came out of that. Fast and slow nodes, there's actually a blog post for Chartbeat. Okay, there's a long URL, you can't read it in back, but if you're interested, search for Chartbeat, fast, slow nodes, it's the first thing that comes up. Tweak one thing and monitor it. Tweak one thing at a time and monitor it. So there's this great session from Elasticon, I think it was this year, by two guys, Dahlquist and Schneider. I don't know what their first names were, but they basically did 4 scenarios, and they changed one thing each time. They looked at storage, and they looked at shard size, or something else. And they changed one thing at a time, looked at the results, and verified, okay, we're on the right track. Let's do one more experiment. Check and verify, and continue on. Tweak one thing at a time. Now, that was one of those other things that we kind of screwed up on that beginning, because we changed all sorts of stuff, and when it didn't quite work, we changed a whole bunch of other stuff, found out that it works better, but it would be really nice to know, okay, which was the one thing that was better. And so we had to kind of recreate our experiments to find out how do we tweak it right in our environment. So how am I doing? 8 o'clock, awesome. Because that brings me to the end of this session. So again, my name is Matt Williams. I'm the evangelist here at Datadog. Matt Williams, or Matt.Williams, or MattW at datadoghq.com, at Technoevangelist on Twitter. We've got beer, and if you don't drink it, the salespeople tomorrow will be very happy. The sales managers will be very upset. But it is Friday, so maybe it's all part of the weekend. There's KO pies, probably enough for a second one to take home. I don't know. I think we bought like 70. There's still a lot left. So eat up. We don't mind if you hang. Well, maybe we do. We might be happy with you hanging out and stuffing your face. What else? What else? We are hiring. Hey, I didn't. Oh, there's a question in the back.
Yes. We started playing with Elasticsearch, and one of our experiences it likes
I
memory.
can't hear anything you're saying, so I'm going to come back here.
Okay, great. Elasticsearch seems to like memory.
Yes.
Can you tell a bit about the infrastructure behind your massive operation?
Like how much memory we
I
have
don't know,
per
what
node.
kind of environment
I don't think I can.
you can.
So, why
Why did we use Kafka?
Yeah. Why did we use Kafka? So that was the stage just before Logstash, and we were ingesting so many events. Say 16 million per second, up to 16, maybe 20 million per second. And based on our configuration, we were running into limits that we just couldn't stuff that much into Logstash. And so Kafka was basically this queue. And we create this queue, and as we send as much as we can to Logstash, and then we send some more, and gradually Logstash would catch up. I believe that was actually one of those issues with how we configured it originally, and maybe now we could pull that out, but it works. Yeah?
Can you talk a bit about how do you plan for disaster recovery, like package?
I cannot. I don't know that stuff. But hey, do you take a large, extra large, or medium? Sure, okay. I'm going to go actually with large because our certs are really small. So because I can't answer that question, I'm going to bribe you with a shirt. Because that's the way out of answering questions.
Would you be willing to share your slides on the meetup.com site?
I would love to share my slides on the meetup.com website. There you go. Other questions? Back in the back corner.
Question about your fast, slow, super slow. You mentioned S3s at some point about logging that are older than 6 days.
Yes.
So I assume it's still in Elasticsearch.
It's shoved out and put into S3.
Oh. So
after the 6 days.
So it's not part of Elasticsearch anymore?
No, it's not. But at that point, if you need access to the data, well, you need to come up with some other way of getting to the data.
Okay. Yeah. I had a question maybe like you could have used that as a storage for Elasticsearch, and I wanted to know what you expected.
Yeah, I don't know enough.
Super bad, but
yeah, I think the big thing there was we'd love to. It gets expensive, so I think we might look into other ways of dealing with that going forward.
Elasticsearch Cloud.
Huh? Yes. A question here.
Well, this is my first time to this meetup, so
Okay.
I don't have from the beginning Elasticsearch of the.
I am the smartest person who's ever spoken here because.
So I don't know what Elasticsearch are actually used for. From your description, I get it from like you are searching for log, but your example concentrate on the JVM, sort of like a Java environment, and that is leading me to how is this going to be useful in real life? How is that Microsoft log is going to be contaminated in this environment?
So we use Elastic for bringing in log information and event information from internally from all the applications that we write inside the company that do all the things that become the Datadog app. And then the developers are able to search Elasticsearch is a big search engine with more than that, but I can search for all my log information through that. But if you look on the Elasticsearch website, they'll talk about doing sentiment analysis in the Twitter stream or recommendations on e-commerce sites and all sorts of other things, and like all sorts of things. So Elasticsearch will do whatever you want to do.
Oh, okay, so you are
and we're applying it to one very specific scenario.
Well, we have some guys from Elasticsearch here, so if
there are
questions about all the different things you can do with it.
Okay.
Yeah, I'm like holding myself down in my seat. We can talk after for sure.
So I apologize.
No, please. Anyone else? Okay.
Why don't you use percolators for alerting? Why do you do queries instead of merge?
I don't know.
I think a lot of people end up doing that for scale. So if you're doing percolation, basically a percolator is a way to do per document like checking. So you add a bunch of queries to Elasticsearch, and then you add one document. You say, does this document match any of the saved queries? And it's great. It's like a really simple functionality. You have a document, you post it, and it says, did it match? But you have to do that for every document. And so if you're indexing hundreds of thousands of documents per second, it's hundreds of thousands of documents that have to be checked across all of the queries. And if you sort of flip the model and you say, well, why don't I just add those documents to the index and use Elasticsearch to query for those queries periodically, you're essentially using the pre-indexed documents that you've already got. And you're essentially only indexing each document one time. With the percolator, we're sort of like taking your one document, creating a single document index and running all the queries against it, kind of, sort of, and then giving you the answer. And so you're doing a tremendous amount of additional work. But in some use cases you have to, so it's a great tool for that. In other cases, like our Watcher product is more schedule-based, where you would say, I want to run this query periodically, and if I get n number of results, take some kind of action. Like, that's a different model.
So you take advantage of the refresh rate, basically.
Exactly. So you're taking advantage of the index that we're building, and so it's already queryable. It's already ready to have that question asked and be answered. But just you have both options. I mean, both are totally viable approaches. It's just depending on the scale you're at, it gets really, really hard. And some people have pushed Percolator and have custom builds of it and things. And it's craziness, but it's because their use case demands it. But many other use cases don't. Most don't. When you get to some sort of scale, so it's straight up.
Also, when you use percolation, your scope is limited to a single document. So you can take a look at the document to decide is it good or bad. When you run a query, in case of Watcher, for example, or in case of you can actually have much bigger scope, and you can say, okay, is the response time for this document significantly bigger than average response time across all documents in the last 5 minutes, for example. So there's different types of questions that you can ask by running queries periodically versus percolating.
Right. Like, what's the 95th percentile of my response time? Right, and that would be a great question that you can't answer.
I'm just noticing that there's some stickers up here, and as you can see, I'm missing a few spaces, so I'm very excited about this. Hey, sir. All right. Any other questions from anyone else? No? Going once? Going twice? Okay, cool. So thanks so much.
Please, guys, if you want to share your use case, if you want to come and present, we'd love to have you. So email us. Thanks a lot. We've got some elastic shirts if anybody wants.